Okay, let's go ahead and start. Last time we got talking about chapter 4, but video crashed, so I'm going to recap some items that we went over before we talk about new material. Up here on top page 148, it talks about logic circuits for digital systems may be combinational or sequential. A logic circuit is combinational if its outputs at any time are a function of only the present inputs. A combinational circuit performs an operation that can be specified logically by a set of Boolean functions. In contrast, sequential circuits employ storage elements in addition to logic gates. Their outputs are a function of the inputs and state of the storage elements. Because the state of the storage elements is a function of previous inputs to the circuit, the outputs of a sequential circuit depend at any time not only on the present values of inputs, but also on past inputs. And the circuit behavior must be specified by a time sequence of inputs and internal states. And it talks about sequential circuits or the building blocks of digital systems are discussed in more detail in chapters 5 and 8. And down here we have a diagram of our combinational circuit. And it says for n input variables, there are 2 to the n possible combinations of the binary outputs. As each one of these comes in with 2 possibilities, 1 or 0. Oh, and remember last time we talked about that typically we're talking about a voltage there. This is where it's, remember where it's used at. There are several combinational circuits that are employed extensively in the design of digital systems. Circuits available in integrated circuits and are classified as standard components. They perform specific digital functions commonly needed in the design of digital systems. And then it talks about how in this chapter we're going to talk about adders, subtractors, comparators, decoders, encoders, and multiplexers. These components are available in integrated circuits such as medium scale integration circuits, MSI. Also in standard cells and complex, very large scale integrated, VLSI. Now our analysis of combinational circuits. Analysis of a combinational circuit determines its functionality, that is a logic function that the circuit implements. You start with a given logic diagram, and you end up with a set of Boolean functions, truth table, or possibly an explanation of the circuit operation. First step in analysis of a circuit is to make sure that it is combinational and not sequential. The logic diagram of a combinational circuit has logic gates with no feedback paths or memory elements. If you're wondering what in the world are they talking about? Over here, you have your inputs coming in, and they form this. They go into this combinational circuit to help form its design, and you have outputs coming in. But then you also have an output coming out here that eventually comes back in as input. So it's a continuous feed to itself. So that's what they're referring to there. Here's another one. You get your inputs coming in here, and then your outputs, but then the output from this combinational circuit comes through these flip-flops, and circles background is back to input. I think that picture probably helps point out the biggest difference between your sequential and your combinational. Does that make sense, the difference between the two? Okay. Yeah, the words here just doesn't really show it, but if you see a picture, then it's, oh yeah, okay, I see it. Feeds back in and uses some kind of memory element. Okay. Once the logic diagram is verified to be that of a combinational circuit, one can proceed to obtain the output Boolean functions or the truth table. I hope today's video doesn't bomb off. To obtain the output Boolean function of a combinational circuit from this logic diagram, we proceed as follows. With arbitrary but meaningful symbols, label the outputs of all gates whose inputs include at least one input of the circuit. Determine the Boolean functions for each gate output. Label gates that are functions of input variables and previously labeled gates with other arbitrary symbols. Find Boolean function for these gates. Then repeat the process outlined in step 2 until the output of the circuits are obtained, and by repeated substitution of previously defined functions, obtain the output Boolean functions in terms of input variables. Basically, we're down here, and we got F1 right here, which is formed from T3 and T2. Well, we don't want T2 and T3 in our final answer. We want just A, B's, and C's, or the complement of those. That's our inputs. So that's what we're talking about, working backwards. T1, as we mentioned, is right here. It's A or B or C, which is this G1 right here. T2, which is right here, is A and B and C. So again, those three come in, and there's an and there. Then we got our F2, which is over here. Over here. And then it's AB. So here's a B coming down, so that's this one. Or AC, which should be this one. Or BC, which would be that one. Then they consider T3, which is not F2 and T1. And that comes from this right over here. So not F2 and T1. Clear some of this junk off. Okay, so we got F1 is equal to T3 plus T2. I say using a series of substitutions. So we got F1 is equal to T3 plus T2. The line right above it, T3 is equal to F prime, F prime sub 2 at T1. So this is going to be replaced as F prime sub 2, T1, or T2. And then going back to the previous page, they tell us T2 is ABC. So A, B, C. And T1, if I'm looking at that right. So this right here is A plus B plus C plus ABC. And then this F prime sub 2. Well, F sub 2 is going to be A and B, or A and C, or B and C. And everything else carries down. Then from, I think it's De Morgan's law, this, we can flip them. A and B becomes A prime plus B prime, not A or not B. This AC here becomes A prime plus C prime. And this BC here becomes B prime or C prime. Um, I'm not sure where this is at. Not finding it anyway. But it's kind of weird the way this is designed and so forth. But we have this right here, and it's going to be equal to yeah, I can't do that in any slick way. I don't see any way to simplify this over here besides brute force. Okay, so this, I can rewrite this as A prime or B prime C prime. Don't remember where the rule's at, but it says if these are the same, and then you got plus or an or in here, then you can do your A prime comes down, or, and then these two, when it appears like multiplied together, though they really end. I don't think there's anything to do there. So that's just multiply them together. B prime times A is A B prime. B prime times B. B prime times C. C prime times A. Oops. A C prime. C prime times B, or B C prime. And C prime times C. And then plus ABC. Now we got B prime and B. This is on page 47. This is going to equal 0. And this is going to equal 0 from postulate 5b. So drop away basically. So I got not A or not B and C prime. So then I got A, B prime plus B prime C plus A C prime plus B prime C prime plus ABC. Then just write down the answer. I don't want to explain how they get it, but I don't see there's anything I could do. Actually, these both have B primes, don't they? Except for that, would just put it back in multiplication form. I want these all to be brute force. Maybe that's brute force is it. Okay, A prime times A B prime. I got A prime A B prime. A prime times B prime C. I got A prime B prime C. A prime times A C prime is A prime A C prime. A prime times B C prime. Then I'll take B prime C prime times A B prime, which gives me A B prime C prime. B prime C prime times B prime C is B prime C prime and C. B prime C prime times A C prime is A B prime C prime C prime. B prime C prime times B C prime is B prime C prime C prime. plus ABC. Now, this right here has an A prime A in there, and from that one page, it says that gives us 0, page 47. So that's going to drop away. This will drop away. That'll drop away. So we're left with A prime B prime C plus A prime B C prime. Now B prime times B prime from page 47, if they're the same, you can drop one of them. So that becomes A B prime C prime. Here they're the same, so it drops away, and that gives us B prime. Oops, that drops away. C prime C is that gives us 0, so that drops away. And this would be A B prime C prime, and this would be ABC. Let's see if that's what they got. A B prime C prime, A prime. I got 5. Some of these might be the same. Those two are the same, which means I can drop one of them. So it gives us A prime B prime C plus A prime B C prime plus A B prime C prime plus ABC. Okay, A B prime C prime, A prime B prime C, which is that, A prime B C prime. Okay, it checks with what they have in the book. That's how you get that with showing all the steps. Is there any questions on that example? Okay. And that's just what we did here. Plug these back in, simplify it down until you got these. There were deriving. Boy, I'm not sure that word. Derivation, I think. Let me see. Derivation. Okay. I had to try this one. Carefully sought out, rare, exotic, obscure, elegant. Okay. Anyway, to get truth table for a circuit is a straightforward process once the output Boolean function is known. To obtain truth table directly from the logic diagram without going through the derivations of Boolean functions, we proceed as follows. Determine number of input variables in circuit for n inputs, form the 2 to the n possible input combinations, and list the binary numbers from 0 to 2n minus 1 in table. Label the outputs of the selected gates with arbitrary symbols. Obtain the truth table for the purpose of the gates, whose set of inputs consists of only inputs of the circuit. And proceed to obtain the truth table for the computer for the output of those gates, which are a function of previously defined values into a columns where all outputs are determined. So here we got our A, B, C, and our input. Across top here we have our T's and our F's. So you need both of them to trace it through. Oh, okay, never mind. I was thinking this had something to do with this up here, but they don't. Okay, so this says analyze the logic diagram in this, find a Boolean expression for F1 and F2. We'll start with F1. And F1 is this right down here. And we got an OR, and that's coming out as T1. So T1 or T3. Well, then I need to go back and find out what T1 and T3 are. And keep in mind, the OR becomes a plus. So T1 is right here, and it looks like it brings in A, B, C. This plus T3. T3 is right here, and it's coming out to G8, which should be T2 and not F2. Now ABC is fine, so we won't touch it. But I need to write down what T2 is. T2 is right here. Looks like it's an AND. So an AND between A, B, and C. So that becomes ABC. And F prime, F2, is right here. And that's coming in from G6, which is G or G3 or G4 or G5. So that's an OR. Okay, so that's that one right there. Okay, ABC is fine here, ABC is fine there. Temporarily. G3. G3 is right here, and looks like it's an AND based upon A and B. That'd be AB. The G4 G4 is right here. It looks like an or. And it's this one, which is A, and it's this one, which is C. So A or C. And G5 is an and it brings in B and C. Got messed up on T1. Double checking my work. That should be A or B or C. T3. Check T3. T2, not F2. Okay, that's fine. T2, A and B and C. Okay, so that's that. T2. T2, ABC, so that's fine. F prime of 2. Stand up for just a minute. Prime. Two fours, where De Morgan's law is. this would give us A or B or C or A, B, C. Then plus is in here from De Morgan's law, says that gets rewritten into prime. Gets rewritten as A prime as A, B prime, A plus C prime, and B, C prime. Is this A or B or C, or A and B and C? And this is going to equal to A prime plus B prime. This is equal to X prime Y prime, or A prime B prime, or A prime C prime, sorry. And then this, from De Morgan's law again, says that's going to become B prime or C prime. Let's see, A or B or C. Unfortunately, in the book, I don't see where they well, they skip a lot of steps, but we'll multiply it all through. ABC times A prime would give me A prime B C, which dropped away because A and A prime is 0. ABC times B prime, B prime there, which means this B and B prime will give you 0, so it drops away. Okay, then these. A prime, C prime, B prime would be A prime, B prime, C prime. A prime, C prime times C prime would be A, C prime, C prime. From De Morgan's law, that becomes C prime or A prime, B prime, and since these are two C primes, I dropped one of them, that's just A. Just A. Where did I get that at? A prime A, B prime, C prime. So give me 0. We left the C prime here. The answer should be A or B or C. So this is what it should be equal to. You see where we're all wrong? I can see where this goes to 0, drops away, but I don't see how the C prime drops away. Okay, I'm gonna cheat and use their little. I was hoping just to look at it to see it, but maybe you do need to write it down. Let me just do that. Okay, F1 is equal to T1 or T3. T1 is equal to A and, or that's an or again, A or B or C. T3 is equal to T2 and that's F2, so it's F prime of 2. I don't have T2 yet. T2 is equal to A and B and C. Um, back to that. F of 2 is equal to A, B, and A, C. This one's BC prime. Okay, so if I start with this one right here, assuming I get them all written down. That's T1, which is A plus B plus C, plus T3, which is T2 F prime of 2. A, B, and C are fine. T2 is A, B, C. T2. Yeah, A, B, C. Yeah, this is shaped a little bit different. F, well, just want F prime. I didn't write that down. Actually, this is F prime here. So it'd be AB plus AC plus BC prime. Plus ABC times De Morgan's Law 47. That becomes A prime B prime A prime C prime and B prime C prime. Oops. A prime and A prime is A prime. B prime and B prime is B prime. C prime and C prime is C prime. Which this wouldn't give us 0, which it will give us that right there. Okay, I guess it does make it easier to write out the write out this above. Questions on that one? Okay, enough about that practice exercise. Yeah, F2 would be very similar. Okay, our design procedure. The design of combinational circuits starts from a specification of design objectives, culminates in a logic circuit diagram, or a set of Boolean functions from which logic diagram can be obtained. And you'll see these following steps. From the specification of circuit, determine the required number of inputs and outputs and assign a symbol to each. Derive the truth table and define the required relationship between the inputs and outputs. Obtain the simplified Boolean expression function for each output as a function of the input variables. And draw the logic diagram, verify the correctness design manually or by simulation. Start it again. Need a bigger table. Got too much junk on here. With my hover cam. Okay, this is on the bottom page 153. Availability of a large variety of codes for the same discrete elements of information results in the use of different codes by different digital systems. It is sometimes necessary to use output of one system as input to another. A conversion circuit must be inverted or inserted between two systems if each uses different codes for the same information. Thus, a code converter is a circuit that makes the two systems compatible even though each uses a different binary code. In general, to convert from binary code A to binary code B, the input lines must supply the bit combination elements specified by code A, and the output lines must generate the corresponding bit combination of code B. combinatorial circuit performs transformation by means of logic gates. Okay. BCD. So you have here the input here, BCD, and this is 2 to the third, it's 8. This is 2 squared, which is 4. This is 2 to the first, which 2 to the third, which is 8. 2 squared, which is 4. 2 to the first 2, and then 0. 2 to the 0 will be 1. That's the 8421 over here for BCD. Output access 3 code 0011. 0. There it is. 0011 is up here, which corresponds to that. Okay, so we got a truth table for both. Um, okay, I better read it. I'm not seeing where these are coming from. Okay. To convert from binary code A to binary code B, the input lines must supply the bit combination of elements specified by code A. And the output lines must generate the corresponding bit combination of code B. Combinational circuits perform this transformation by means of logic gates. The design procedure will be illustrated by example. It converts BCD to XS3 code for the decimal digits. The bit combination assigned to the BCD and XS3 codes are listed. Since each code uses 4 bits to represent a decimal digit, the converter must have 4 input variables and 4 output variables. We designate the 4 input binary variables by the symbols A, B, C, and D. And the 4 output variables by W, X, Y, and Z. True table selecting the input and output is shown in table 4.2. The bit combinations for the inputs and the corresponding outputs are obtained directly from section 1.7. Notice that 4 binary variables may have a 1.7. Okay, that's what they're talking about. Okay, I see. Maps in figure 4.3 are applied to obtain a simplified Boolean function. Let's see, this is okay. I think I see where everything comes from. If I look over here at the ones that give us 1, or give us ones here, I should say, because this is our output. The ones here, this would be 0, 0, 0, 4 zeros, which would be this one right here. This one gives us a 1 here, which would be 0, 0, 1, 0. 0, 0, 1, 0 would be this one right here. Next one that gives us 1 is this one right here, which is 0, 1, 0, 0. 0, 1, 0, 0 will be the 1 there. Z is equal to 1, and then I'm going to look in A, B, C, D. Okay, I see that they're doing the conversion for each one individually. So W, X, Y, and Z. So here I'm going to look where Y is equal to 1. Y is equal to 1 here, so we'd have 4 zeros. And 0, 0, 0, 0, we put a 1 there. For y is equal to 1 right here, tells me to use these two. Those are zeros. So 0, 0, 1, 1, which is right here, which is 1. Does that make sense where all those ones come from? That's our z. This is our y. This is our x. That's our w. Okay, so after you get those, these are don't care. So I combine these 4 with these 4. There's 8 of them, which is okay. That's 2 to the power. And I come straight over here, straight over here, straight over here, straight over here. It counts for both A and B. If I come straight up, this is C is equal to 0. This is C is equal to 1. So that counts for that. But here I got D is equal to 0. D is equal to 0, which is our D prime, which is where that comes from. This one, I group these 4 together and these 4 together. This one is come straight over here. All that disappears. CD is right here. C prime D prime is 0, 0. Okay. And they just go through and do the same kind of breakdown that we saw before. And then they work backwards. They start at D prime. They start plugging in all values and get down to here. Come over here. And our first one is Z is equal to D prime. Here's D, goes to an inverter, and comes over here to Z. Our next one is C and D, or C or D prime. C and D coming into there. There's an OR here. And C or D, the prime, comes in there. That's where that one comes from. B prime C or B prime C, this is for X. B coming in there, so that's B prime. C. Okay, I'm having trouble seeing this one. Let me write it down. X equals B prime C plus B prime D plus B C prime D prime. Here's X coming in, and here's an OR. But right away, what catches my eye is there's only two lines coming into it. Okay. Maybe I have to do a lot of simplifying or something. See how I interpret this. Okay, so there's no OR here. Start with the easier one, the second one. And that's an and it's coming from B, so that's an inverter, B prime. The other one's coming from that line, which is going up there, which is an OR, which is D or C. Okay, so this first one is coming from B, definitely, and C plus D prime, which is B, C prime, D prime. If I go read Morgan's Law, just make sure I get that right. Okay, 47. Okay, so that would be C prime D prime from Morgan's Law plus that'd be B prime D plus B prime C which would be B C prime D prime plus B prime D plus B prime C, which is what they have. Okay, I agree with that then. Boy, these are just not such you can look at them and just easily see it. Okay. The logic diagram implements these expressions as shown in figure 4.4, which we just looked at. Note that the OR gate whose output is C or D has been used to implement partially each of these outputs. Not counting input inverters, the implementation in some products form requires 7 AND gates and 3 OR gates. The implementation of figure 4.4 requires 4 AND gates, 4 OR gates, and 1 inverter. If only the normal inputs available, the first implementation will require inverters for variables B, C, and D, and the second implementation will require inverters for variables B and D. Thus, the 3-level logic circuit requires fewer gates, all of which in turn require no more than 2 inputs. In general, multi-level logic circuits, exploit circuits, subcircuits can be used to form more than one output. Here, 8 or C or D is used in formatting X, Y, and W. Result is a circuit with fewer gates. Logic synthesis tools automatically find and exploit subcircuits that are used by multiple outputs. Okay, let's take a look at binary adders, subtractors. Really long section here, but it's so long that we might as well get started on it. It might be if I do a little bit right now, it might be the entire next time, though, based on how lengthy this seems. But it depends how fast it goes. Okay, digital computers perform a variety of information processing tasks among functions encountered with various arithmetic operations. Most basic arithmetic operation is the addition of 2 binary digits. A simple addition consists of 4 possible elementary operations. 0 plus 0 is equal to 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 and 1 is equal to 1, 0. First 3 operations produce a sum of 1 digit, but when both augend and addend bits are equal to 1, the binary sum consists of 2 digits. Higher significant bit of this digit, the carry obtained from addition 2 bits is added to the next higher order. Next higher order pair of significant bits. A combinational circuit that performs addition of 2 bits is called a half adder. One that performs addition of 3 bits, 2 significant bits, and a previous carry is a full adder. Okay, half adder. In the verbal explanation of half adder, we find that the circuit needs 2 binary inputs and 2 binary outputs. That's our X and Y are inputs, and C and S are outputs. The S is your sum, and the C is your carry. Well, I'm not clever enough to see it. But to simplify Boolean functions for the last 2 outputs can be obtained directly from the truth table. I can see C. Because if you look at 0, 0, 0, 1, 1, 0, all give you 0. 1 and 1 gives you 1. Well, this is like when we're multiplying them together. 0 times 0, 0, 0 times 1, 0, 1 times 0, 0, 1 times 1 is 1. And it tells that. They say the carryover bit is equal to X and Y, as in multiplication. Now here they tell us this. And I can see S by building a little bit more to the table, but I don't think there's any way I could see that from without the answer given to me directly. So we got X and Y, 0, 0, 1, 1, 0, 1, 0, 1. I need X prime and I need Y prime. X prime would be 1, 1, 0, 0. Y prime would be 1, 0, 1, 0. I need X prime Y. So X and Y, X prime and Y, multiply these together. 0 times 1, 0. 1 times 1 is 1. 0 times 0, 0. 1 times 0 is 0. And then X, Y prime. I'll take this one and multiply it times this one. 0, 0 times 1, 0. 0 times 0 is 0. 1 times 1 is 1. 1 times 0 is 0. It's like you're adding these together. 0 plus 0 is 0. 1 plus 1, or 1 plus 0 is 1. 0 plus 1 is 1, 0, which matches our S column. If you can see that directly, that's fantastic. But I can take the form of it and work backwards and see where it comes from. But their implementation is simplified Boolean function for the two outputs can be obtained directly from the truth table. Oh well. Now implementing it, S is a X prime Y, X prime, there's X prime, Y, there's a plus, or X, Y prime. C would be X and Y. Should give you that. Second. Oh. That makes sense on the half adder. I realize that everything we do, like if you're adding numbers together, if you change in the binary, because there are voltage, and you're working with this, what they're talking about is implemented from a circuit standpoint. If we started with these two bits, 1 and 1, then that'd give me 0 with a carry of Let's see, 1 and 1. Carry of 1. And then I would handle these 2 bits, take into account that that carryover. Then I'll give you a diagram of that, but you'd have to handle that carry in an appropriate way. I don't see a picture of it. This is the closest that we get from what I can see. So you have these coming into an adder, and that's giving you the result S here. And then the carry it'd probably be better if they did this a little bit different. Oh, they do label it. Okay. See, here's the P naught, which is coming over here, carrying over to there, and then coming into here. When we get to this point, we might actually do an example so we can see how that's working. Actually, with the number example, go with it. Okay, full adder. Grab a drink. Addition of n-bit binary numbers requires use of a full adder. And the process of addition proceeds on a bit-by-bit basis, right to left, beginning with the least significant bit. After the least significant bit, addition to each position not only adds the respective bits, but also does the carryover. 0 plus 0 plus 0 is 0, carry the 0. 0 plus 0 is 1, plus 1 is 1, carry over 0. Same thing here. 0 plus 1 plus 1 is 1 plus 1 is 2, so you put a 0, carry the 1. 1 plus 0 is 1, and carry a 0. 1 plus 0 plus 1 is 2, so we put a 0, carry the 1. Same thing here. And here, 1 plus 1 plus 1 is 3. So you put a 1, carry the 1. So if I come over here, these 1s probably correspond to S, I'm assuming. Let me see if that's a true statement. S being 1 is 0, 0, 1. 0, 0, 1, which would be right there. It's okay. Next one is 0, 1, 0. 0, 1, 0, which is 1 there. Next one's 1, 0, 0. 1, 0, 0 is a 1 there. Next one is 1, 1, 1, which should be right there. So these are where S is equal to 1. Now, at this point, you can't pair any of these together, so you just have 4 separate terms. This one, I'm assuming is where C is equal to 1. Let me see. 0, 1, 1, 0, 1, 1, yeah. 1, 0, 1, 1, 0, 1, yeah. 1, 1, 0, 1, 1, 0, yeah. And 1, 1, 1, 1, 1, 1. Okay. Group these two together, group these two together, group these two together. These two here would be XY, which is this one. This vertical pairing would be YZ, which is this one. And this pairing here would be X Y. Oops, wait a minute. Okay, XZ. No, it's okay. This is XZ, which is that one. This one is YZ, which is that one. Then this is XY, which is that one. Okay. So that's where they get all those. Okay, S is equal to this, C is equal to this. So this is what we want to implement. And they indicate you can use the exclusive OR gate. So that's what they're referring to down here with the little plus circle around it. So there are XOR. No, that isn't XOR. Never mind. The XOR has a line further apart from the OR gate here. Okay, so that's just an OR with an extra extended line, which is S. So that's those 4 terms on this previous page. 4 right there. C is the ORing of those ones, which is what we got right down here. Don't think they have right. Oh, I'm looking at the wrong one. This one up here. Okay, I can buy that. Because there's no primes up there. I was looking down here. And none of these have primes on here. So, okay, that makes sense. Here's our implementation using the full adder with 2 half adders and the OR gate. So that's based upon, let's say, this XOR here. Then on page 160, it talks about binary adders. It says binary adder is a digital circuit produces the arithmetic sum of two binary numbers. It can be constructed with full adders connected in cascade, with the output carry from each full adder connected to an input carry of the next full adder. This would correspond if we're adding the number 1011 and 0011 together. So you got those here. And we're looking at A0 and B0 coming in. So we're strictly looking at these two right here. Okay, so those two are coming in. So we got 1 and 1. Now we have a C0 coming in here, and I'm not sure if I fully understand that part. No matter what, the carryover, since there's no previous digits, has to be 0. So not sure if I understand why that has to come in like that, unless it's just the design of an adder where it has two inputs coming in, and you have your carry coming in, and then you have your sum going out. There might not be no way to nullify this. Okay, 1 plus 1 is 0, and then I want to carry the 1. So this is giving me 0 coming down here, and then this is bringing a 1 over to here. So then here we're bringing this next two digits, 1 and 1. So this is 1, this is 1, our carry was 1. 1 plus 1 plus 1 is 3, so we'll have a 1 come out here, that's the S, which is right here, and then we'll have a carryover 1 coming over. There's our carryover. Now we have B2 and B2 and A2 coming in, which are both zeros. So here's 0, here's 0, here's 1. 0 plus 1 is 1. So I have the 1 coming out here, and then my C3 be 0. That's where the C3 is coming through. And then at that point, we have A and B. So we have 1 and 0 coming in. We said this is 0. 0 plus 1 plus 0 is 1, with a carryover of 0. And that's the design of the 4-bit adder. It says a 4-bit adder is a typical example of a standard component that can be used in many applications involving arithmetic operations. Observe that design of the circuit by the classical method would require a truth table with 2 to the 9th equals 512 entries, since there are 9 inputs to the circuit. Okay, I see it. Because here you have oh, they don't mean this. They don't mean this way. A different way. You have 4 of them coming in, 2 to the 4th. Then you have another 2 to the 4th coming in for both A and B, so that's 2 to the 8th, and then carry, which would be 2 to the 9th. Okay. Carry propagation. Addition of two binary numbers in parallel implies that the bits of the OGN and IAD end are available for computation at the same time. As in any combinational circuit, the signal must propagate through the gates before the correct output sums is available in the output terminals. Total propagation time is equal to propagation delay of a typical gate times the number of gate levels in each circuit. I think we're going to stop there because I think this talking about carrier propagation is going to be more than I can get through in about 9 minutes. Plus, I feel good that I understand this pretty good. I don't think I understood adders completely the first time I taught this course. Now they're making perfect sense. Another 3 or 4 years, I'll have this down pat. Is there any questions on any of that? Okay, I'll go ahead and stop recording.